Hey folks, can you hear me?
Yes, sir. Good morning, sir. Good morning.
Good morning.
We can
How are
hear
you
you,
doing?
sir. You're fine, sir.
Okay. Let me
We'll
know
start
when we...
within 2-3 minutes, sir.
Okay, just keep me posted. I'll start whenever you guys are ready.
Okay.
Microphone is muted.
Okay.
How are you, sir?
Doing very well, Anuj. Tell me.
So just get started.
Okay. Should I share my screen? Try sharing my screen then. Okay. Let me see. Ashish, I think it's asking me to quit and reopen. So just give me a second. I'll quit and reopen the thing.
Sure, sir. Sure.
Can you see my screen?
Yes, sir.
Yes, I can.
Okay. Can I get started now?
Shaim, sir?
Yeah.
Can I get started? Are we good?
No, sir. We will start, sir.
Okay. So, hello folks.
Wait for a moment, sir. We
Wait for a
have
few
some
minutes.
welcome speech.
Okay, okay.
Yeah. So we have some introductory speech.
Morning, present here. It gives me immense pleasure to welcome you all to the 33rd talk of Transtech Research Talk series organized by KSCSTE National Transportation Planning and Research Center NATPAC. Before delving deeper, let me take a few moments to enlighten about the institute. NATPAC is a premier research institution functioning under the Kerala State Council for Science, Technology and Development, spearheading transportation research including transportation planning, traffic engineering, pavement engineering, highway design, road safety, intelligent transportation systems, inland water transport, etc., and promote sustainable development initiatives to mitigate traffic and transportation challenges faced by the state of Kerala. This talk series is yet another unique venture of NATPAC designed to explore diverse topics from cutting-edge technologies to sustainable solutions. Here we will be featuring eminent researchers who will share their expertise and valuable insights, inspiring future research and developments in the transportation sector. Today we have with us Dr. Anuj Sharma, Professor, Department of Civil, Construction and Environmental Engineering, Iowa State University, for sharing his valuable insights on the topic, leveraging CAV data for scalable signal retiming, signal IQ framework. Now I request Dr. Shahimas, Principal Scientist, to deliver the welcome address.
Good morning, sir. On behalf of KSCSTE-NATPAC, I am delighted to welcome you to the 33rd Transtech Talk series, our monthly global knowledge forum held on the second Friday of every month, featuring leading experts from across the transportation sector. Since its launch in February 2023, the series has hosted distinguished speakers, including Professor Tom V. Matthew, Dr. Srinivas S. Pulgirtha, Dr. Rajiv B. Malik, Professor R. Jayakrishnan, and many other eminent researchers and practitioners. Today marks the 33rd talk in the series organized by NATPAC's Transportation Planning Division, we are honored to host Dr. Anuj Sharma, professor at Iowa State University, who will speak on leveraging CAV data for scalable signal retiming, the signal IQ framework. Following the presentation, we will open the floor for a question and answer session, and we encourage all participants to engage actively. Thank you for joining us. Please join me in extending a warm welcome to Dr. Anuj Sharma.
Thank you, sir, for the welcome note. Now, I would like to invite Sri Anish Kini, Senior Scientist, to introduce the speaker to the audience.
Thank you, Ashwati. Sharma, Professor, Department of Civil Construction and Environmental Engineering, Iowa State University, where he serves as Associate Director of the Translational AI Center and Co-Director of the Reactor Laboratory at the Institute for Transportation. His research focuses on applying artificial intelligence, connected vehicle data, and large-scale analytics to improve transportation system safety, mobility, and operational efficiency. Dr. Sharma has projects totaling over $20 million from federal, state, and industry sponsors, NSF, FH, and state departments of transportation. His current work includes developing the Signal IQ platform, an AI-driven tool for automated traffic signal performance monitoring and retiming using CAV data.
Thank you, sir, for the introduction. Now, I would like to invite our speaker to deliver the talk.
Over to Anuj Sharma, sir.
Thank you for the invitation. I am really happy to make this presentation, and feel free to ask me questions even during my talk if there are any questions. Otherwise, we'll have a discussion towards the end as well. The big reason for giving this talk is that as we are moving through times, the amount of data which is becoming available is increasing significantly as well. We have access to the video data coming in. We have access to data in terms of Twitter feeds and cloud-based data available. We also have data coming from telematics of various vehicles driving on our road. So as we previously, when we were operating traffic signals, the data was coming usually from one source, which was probably inductive loop detectors on the roadway. So with all this data coming into place, the reason for such jump in the amount of data which we have access to, there are three basic reasons why this is happening. One is that the cost of compute is going down significantly. To just give you an idea, that if you would have bought something which had power of an iPad in 1940s or 1950s, it would have costed you millions of dollars. But today you can get it just for the price of maybe a few $100s. The other big thing is that even the cost of sending this data over wire or even wirelessly has gone down significantly. As you would know that the cost of communication has dropped. In 1999, if you had to send around 1000 Mbps, you would be paying around $1,200. But today you can almost get it for $10-15. So which means that people are not only able to process the data on the edge by cheap compute, they're also able to transmit a lot of this data. And what it has enabled is ability for the cars to start communicating and becoming the sensors themselves, because now a lot of these cars are sending back information to their OEMs, and which are packaging and selling this information. The final thing is once these devices are sending the data back to us, the cost of storing this data has also significantly reduced. As you can see, that if you went out in the market to buy a terabyte hard drive, even 10 years back, it was pretty cost prohibitive, but now they are coming for $100. So not only can you process the data on the edge to collect a lot more data, you can transmit it for a very cheap price, but you can also save over multiple years of data without spending a fortune. So a lot of agencies, what they have started doing is having access to huge amount of data, which they can process. So just giving an example of state of Iowa. If we were in 2008, we were collecting data from few sensors out there on the road, where we were processing the data, maybe 32,000 rows of data ourselves, and usually one person sitting with an Excel could easily process the data and come up with some solution. But in today's days, if we are getting data from almost 4% of the cars which are on the roadway in the state of Iowa, we are getting around 40 billion rows of data per year, which is very difficult to process using a simple Excel file. So what we need, and one other thing is the data has increased by almost 1,000,000-fold, but the number of people who are available to process that data is still the same. So essentially, we have to start moving away from a person-heavy analysis towards something where we can use automated processing of data and automatic information retrieval to design signal timings. So one of the common processes, and this is not just in US. I have had presentations done in multiple countries like Australia and Europe, and even in India. They're facing the same problem, that although the data is increasing by a significant amount, the workforce to evaluate the data is limited, and also there is a limited budget, so that you cannot just go ahead and say that, hey, I'll put an adaptive system across my corridor. So there has been recently a flurry of tools which are developed in just providing a dashboard for this performance measure, and it is very easy and easy to dump a lot of performance measure on a dashboard and give it to a department or CDC to essentially look at it. But again, we fall back to the same pain point, that the number of people who are there to evaluate this data are limited, and might not have expertise or ability to process all the graphs which are being generated. So this just gives a comparison of what the state of art is today and what we are planning to move the industry towards by Signal IQ. So according to some stats in US, they were claiming that they should have at least one engineer per 100 signals to have it operated at a very optimal and good quality. But usually there is one engineer per 250 to 500 signals. And there is a limited budget to have adaptive systems. So at least in US, we are not going towards 100% adaptive throughout the city. There has been effort done in Australia where they moved towards a completely adaptive system, but at the end of the day, if it's a black box system, it is shut down and it is effectively operated as a time of day mode. So what we want to do with our platform is use the existing set of data. So instead of asking cities to put additional sensors on their system, can we use data coming from telematics of different cars which are already on our system to generate statistics? We are trying to make it a cloud-based solution. So instead of it requiring a lot of edge compute, pushing all the data to the cloud and then and processing it on the cloud is important. And what it does is it scales the system as the city increases, or if we are going to multiple cities. Finally, instead of expert staff being needed to have the system analyzed, we are using AI to analyze the thing and coming up with a goal-based performance metrics and performance signal timing refinement. So I essentially have put this problem in stages where probably we are operating at level 0, where we have some information about the system, but most of the signal timing is done using personnel time, and that is level 0. As we move towards more dashboarding, what I show is that although the signal performance improve, but it requires more personnel to analyze the data from different traffic signals to essentially to essentially come up with a good signal timing plan, and so you require even more people. Level 2 is more where we set some static thresholds so that if a signal is performing worse than a specific threshold, for example, if we say that, hey, if you're having a delay, if the level of service falls below D, just pick up that specific signal and let us know and we'll fix it. That is more threshold based planning. Here also the personal time goes down, but not significantly. And finally, we move towards ML and AI domain for actually improving, reducing this personal time significantly. And finally, in level 5, we can do a full implementation. So what I would like to also show is that it is not good to have a system. Are there any questions? I'm just listening to some. Okay. I'll keep moving. I just wanted to give an example that usually. Please go ahead.
Please continue, sir. There is no question.
Okay. So what I was going to show is one of the use cases where a city implemented adaptive system, but there is a difference between a black box system and something which you can essentially figure out what the system is doing. So in this specific scenario, an adaptive system was implemented by a city in US, and it was implemented on 2 corridors. The objective of the system was to the promise that was made was that the system would be able to better manage the peak periods happening in these specific corridors. One of the things which was found out after the system was deployed for the first time, it actually didn't perform as well as it was promised, and we saw that there was an increase. The orange line on the top left, this orange line is the performance in terms of travel time after the system has been deployed, and blue is when before the system was deployed. So overall, the performance was not that great. It actually was negatively impacted in both eastbound as well as westbound direction, specifically in the peak time. And this is one of the common things which people struggle with, is that they do implement an adaptive system which has been found to be working very well in other places. They put it on their street, and then when they do the analysis, it sometimes doesn't end up performing that well. And the reason for that is there are multiple hyperparameters in this adaptive system, and it is not clear even to the people who are producing these systems how essentially that algorithms would work. And sometimes, although the algorithm seems to be working well in the simulated condition, when you put it in real world, it doesn't work that well. Is there a question? Okay, let me keep going. This when I'm talking about this adaptive system, this did include coordination, and it still performed poorly. And one of the reasons was that most of the adaptive systems which are out there on a single corridors cannot account for oversaturation, and they underestimate the impact they had. So in this specific scenario, it was saturation which kind of really impacted the system and couldn't do better. They went through multiple iterations, but at the end of the day, what they decided was they were not going to have the adaptive control set up during the peak periods, and then they were kind of able to match the performance of the current system. So this is just a story I wanted to tell before we talk about our system. And the impacts on crossroad in this specific scenario was also not that great. So we did analysis of the crossroads as well. The reason was that in this case, the adaptive system was just trying to catch up with the moving demand. And that is one thing people have to be careful when they're implementing the adaptive system is what essentially is the adaptive system doing, and they can get into a big problem there. So the reason why we want to build our system a little bit different than a black box is that the transportation traffic flow theory is based on a lot of these empirical models, and we would like to, instead of throwing away all the empirical models which have been derived in traffic flow theory and other places, we would like to use as much of them as possible because they are based on the so this is not my system. This is a system which was implemented, and in this case, they were not keeping the cycle length constant. They were continuously predicting what the cycle length should be, and implementing the system. So essentially, in that scenario, the system was not performing very well. So one other thing is that why it is important to use some of the theory is that there is less number of latent class, so you don't have to get into a very high latent space to come up with your system design, so you can make the observations and have systems that can make the changes. We do have to have a open instead of black box system and a white box, or at least an explainable AI system. The reason is that if the system fail, there is a need to explain to people what is going on, and then you cannot purely depend on a black box system because there might be an edge case where there is a catastrophic failure, which you cannot have. The other thing which is very important to remember is that the optimization functions for the corridors keep changing. Although when you talk to one corridor manager, they might say that our end goal is to minimize travel time, but there are several different optimizations they like to optimization scenarios they would want to address, which comes out later on. So this is what we were hoping to do with our system when we designed it, and I'll go through the experience as well. One of the biggest thing which we did initially is for any corridor where we are doing data collection or signal retiming, we had a sensor data quality module, which is very relevant because there has been a lot of studies which show that if you are purely dependent on if you are purely dependent on sensors from the roadways, there might be anywhere between 10 to 30% of the sensors which are not functioning well, and if you don't capture that can impact your performance in a system. And then the other thing is the sensor data quality can be measured by using some simple stats whether the sensor is pinging back or not, whether the call is being removed or not. But then you can also start looking at traffic flow theory based measure and to find out whether your sensor is actually behaving as it's supposed to. So before implementing any adaptive system, it is extremely critical to have a module built which is continuously monitoring the sensor quality and identifying the issues where there might be a need for sensor replacement. The other thing which we designed for our system was a module for assigning demand patterns. So in this scenario, what we did was we were looking at the total loading of vehicles on our system and coming up with these cumulative profiles for the whole 0 to 24 hours. And one of the things which we did in this scenario is the first step was to identify days which were event days. Event days are essentially can be there is a work zone on your system which might be causing a very different demand pattern, or it can be heavy rain that can be disrupting your demands. So you don't want to use this if you are using. So our system initially is working towards typical days, non-event days, and then after removing the event, we started grouping how the demand patterns are changing and if there is a cluster of demands on specific days. So in this scenario, we got Monday through Friday had similar demands, and Saturdays and Sundays have had different demand. After we have identified that, then we start looking into creating timing plans for Monday through Friday. For creating the timing plan, we developed something which we are calling demand pattern diagram for both eastbound and for the whole corridor. And what this demand pattern diagram does is it looks at volume to saturation flow rate for the critical intersection, and it plots the stochastic distribution of your S ratio over the whole corridor. There are a couple of important things which this diagram is able to show, and we also overlay the current cycle length on top of this diagram. So one of the things which it can easily show is whether the demand patterns as they are changing over time are essentially um, changing as in terms of time of day cycles. The other thing which we are using this diagram for is also to find out how many of these cycles would be important. So in this case, we once we have found out this demand pattern, we take, depending on what threshold does the city want to use, whether it is 85th percentile VRS ratio or it is 90th percentile VRS ratio. We identify the cycle length based on Webster's, and then we do clustering to find out what cycle length should be implemented so that the number of transitions are low as well. So this is the first step after we have removed the event days. And one other thing which we do is look at the event days, how many event days happen for that street, to also assess whether an adaptive control would be a better option, whether a fully adaptive control would be a better option, or you can have time of day control on that specific site. Finally, we use something called percentage of cycles in platoon to identify what period of time is the coordination needed. In this scenario, what we are doing is essentially looking at vehicles which are near each other to call them platoons, and then identifying what is the platoon length, how many vehicles are present in the platoon, and then how many cycles during the day has that length of platoon available. So essentially average platoon per time of day and the percentage of the cycle that is having some platoon gives you an idea where the coordination would be important. Otherwise you can run the system free and just minimize delay. Then after we have found out the cycle length, which is relevant, and even the time of day patterns which are relevant, we try to optimize offsets. We used a genetic algorithm to optimize the offset. But one of the things which and this is where we were talking about the optimization function. This specific traffic which we are talking about is not heterogeneous. This one is mostly, when I say not heterogeneous, it does involve cars and trucks, but it doesn't involve cyclists and motorbikes that much. This is still in Iowa. So this is something where we have modified the time space diagram, which is commonly used for signal timing, and we have made it more horizontal by moving the time, by subtracting the time between two intersections. And so if you see a green lined up on top of each other, it essentially means that the coordination is going well. So basically our optimization function is trying to do multiple things in this scenario. Our optimization function is trying to maximize the green band, but it is also trying to not allow the stoppages happening next to each other. A significant number of vehicles stopping. Like if I leave a intersection, I don't want that vehicle to stop on the next intersection. The third thing we are trying to explore in this optimization is that there is a minimum amount of bandwidth which is available. So we have fine-tuned this optimization function, but as we have implemented in different cities, we have found out that some of them have some specific constraints which have to be modified. So after GA genetic algorithm produces this diagram, we essentially have an expert fine tune it as well before we implement it. So the question is whether the green bands are different. The green band has to be different because different signals have different side street volumes. So what you see is, like, if you are going from top down, anyone who has so 2 is moving from top down. So anyone who has departed from old highway can go through till it hits the JFK. And what happens here is like, obviously the people who are in the old highway towards the end might have to stop and then come back again, but then at JFK they go through again for their green time. So there is not much we can do to control the amount of green time because of the side street demands, but whenever possible we are letting people go through as much as possible, and then allowing then the other street goes through. So in this case the bandwidth is between the top and the bottom one, but in general that is the idea behind it. So at the end of the day, we produce something similar to this, where we are showing that demand patterns, and then we are showing the current timing plan versus the proposed timing plan. And the color code which you are seeing in the green, in the red, kind of depends on this is adaptive. It is adaptive in the sense that the side street only comes on when there is a demand on the side street. So if you are seeing that there is a light coloration in red, that means that the number of times we saw that red come up is a little bit lower. So so essentially, what you are doing is, instead of having a system which is a black box, every step which you go through and implement can be explained why a specific value is being used, and this becomes easier for a traffic engineer to understand and implement. So we went ahead and what we did was we went ahead and implemented this system in several cities. The first thing which we, before before the fine tuning of the time plan, we wanted to find out which places we should be doing it. We came up with just 4 critical performance measures. Instead of producing 30 or 40 performance measure, we just focused on 4 basic ones. One is split failures, which essentially tells you if the queue is not cleared within 1 green time, that is a split failure. So what percentages of timings are having, what percentage of cycles are having split failure is an important measure. The second measure which we looked at was slowness. Slowness is essentially inverse of travel time. So how much time it takes, inverse of speed. So how much time it takes on an average to cover a mile for a given corridor is slowness. The third one is stop probability. What is the average stop probability of vehicles stopping at your corridor, which gives you an idea how good the progression is. And the third and the final performance measure which we evaluate is called time of day correlation. If the demand pattern which we have found out is corresponding to the cycles which are being implemented, and based on that we prioritize the corridors, and then try to implement our improved signal timings for those corridors. So just to give you an idea how the system works, in this scenario, we ran a pilot on a corridor in Olathe. The cycle lengths were really high than what were needed. So we significantly reduced the cycle length, and you can see that a lot of benefits were derived on the corridor, on the side street, as well as the weighted average delay. And finally, the total savings on this corridor was significantly around 26:1, even when we accounted for the cost of operating this system using cloud computing and getting the data from intersections. So this was pretty significant. Same thing, there were, when we implemented in Ramsey corridor, one of the things is when you are reducing the amount of cycle which you are providing, there can be negative impacts on your main street delays. But if your sites, and again, that brings you back to the objective function. What is your biggest objective function? If your biggest objective function is to do best on your main street and not worry about too many side street, so you have to change your weight functions of your GA to do that. So these are some examples where we have implemented the system. In this case, we were able to both significantly reduce not only the delays, but also improve the performance on the main street. And this was done using, again, the offset optimization. So it is not necessary that this kind of thing has to be done when when there is a little bit of a change in this scenario. Like this is just, this is a new demand pattern which emerged because of COVID, but this can happen because of several things where the demand pattern completely changes and you have to come up with a completely new timing plan, and that is possible using the system as well. One thing which we have started including the system now is if you have cameras present on your system, we have come up with automatic measures of identifying certain failures and including them in the performance measure. So one of the things which we look at is there what percentage of a time a vehicle is spending within an intersection, and if that time is significantly higher, we start detecting that there might be some kind of a split failure. There might be some kind of a queue spillback happening. So especially in scenarios where you are tending towards oversaturation, such detection gives you a very good framework of identifying if there are issues happening which are related with overcongestion in your system. So in that case, as I said, that a lot of system, when they are just purely doing optimization, might not see all the data and can result in even further worsening your system performance. So like using as much data as possible improves your ability to detect such oversaturation spillback, and this might require a different set of optimization function where we are managing queues rather than minimizing delays and operating our system. One other thing which we haven't implemented yet, but we are moving towards it, is assessing performance using traffic conflicts. So this is more related with safety. So in this scenario, we are looking at the trajectories as the camera which is present over there, and if we see close call or near miss accident, we keep a track on that. Currently, we are developing models to find out what thresholds should be used that triggers any response to a signal timing change or any geometric change. But this is a work which is under progress to improve safety at an intersection for improving signal timing. I would like to end with with just a pitch of why near miss accidents, continuous monitoring of near miss crashes can be very relevant at specific signals. This was one of the places where we were doing. We were working on with a state where they had a fatality, and what essentially the city was under the impression is the fatality is happening because people are running the stop sign without stopping. So in this specific scenario, we deployed cameras to identify what is going on at the intersection. Going in the study, we didn't have any idea why this system is having so many fatal crashes. So the first hypothesis was that there might be a number of people who are not coming to a full stop, and what this system The pedestrian signal timing depends on different scenarios where we are running the thing. So if there is pedestrian signals which have to be implemented every cycle, in that case we are just increasing the minimum cycle length and implementing it. But in certain scenarios where the pedestrian demand is low, then we are having a push button. So in that case, again, you have to balance between if you have to do too much of transitioning, your coordination goes away. So there is a balance between whether you want to have a bigger cycle length and accommodate pedestrians in every cycle, then you might have to limit your cycle lengths in optimization. Whereas if you don't have that many pedestrians, then you might have to put a push button there and then disrupt your progression at times where the pedestrian is present. So then the other thing which we looked at was essentially looking at the number of percent times where the stopped vehicles are not completely coming to a full stop was pretty limited. So basically putting the reason that the crashes are happening because of people not stopping when other vehicle is present was not supported by the evidence which we got from this analysis. So we started looking at more videos where we found there was conflict, which means that two vehicles were passing very close to each other. So in this scenario, we saw that, hey, this vehicle comes to a stop over here. The vehicle is waiting for the vehicles from the left to finish their movement. And you see that the vehicle this vehicle has not cleared the intersection, and the vehicle has started already entering the road. There are two important things to know about this specific site is that the direction of Main Street has very high speed traffic. So if the person is focused on just these vehicles which are making the left turn, sometimes they forget to see the other side of the road, and can result in a crash. So this is another similar scenarios. And one of the reasons all these videos came up by using automated processing. So we collected around 3 days of data at these intersections, and then let the video processing find out the places where there was near misses. So this is another near miss identified. In this case, in this specific case, you would see that the vehicle has entered before this vehicle has gone through. But one other thing you would see is there is a vehicle coming on the top side, which this vehicle ignored and went through. So this was a close decision over here. There was one more question: can we do this processing in real time? Yes, it is possible to do this processing in real time. Currently, we are doing real time processing of around 100 cameras using our in-house cluster. But obviously, that cluster can be scaled if your number of cameras are higher. So in this case, again, this red vehicle is waiting for people on the other directions to stop, and it makes a decision to go through after this vehicle goes through. And you would see that as soon as it makes the decision to go through, there obviously is a vehicle on the other direction who had the right of way. In this scenario, you will see the car on the other side making this red car on the other side basically waiting for this black truck to make the movement. So the black truck crosses, the car decides to move through and almost get hit by this vehicle. So essentially, by looking at these near misses, we were able to convince the DOT that the problem is not because people are running the stop sign. The problem is happening because of the fixation of driver in decision making, and them getting fixated on a specific thing which is going on and forgetting about the things have seriously changed in the other directions. So in this scenarios, they decided to put a roundabout in there. But this real-time incident detection can be brought in when you're looking at signal timing. So essentially, to summarize on what we have done so far, we are trying to use as many data sources as available, and not just the CAV data, but also if there is camera data available and things like that, we are trying to use that. We don't want to have any hardware updates done, so that the cost of improvement keeps low. Instead of focusing on coming up with cycle every second, we try to find out which corridors have problems and try to propose solutions to solve those specific problems. And the objectives are defined by the agency instead of we assuming it. One of the things which I'll say in terms of cons is that it is not designed for oversaturated conditions so far. So our optimization functions are focusing on undersaturated scenarios, but can be extended to oversaturated scenarios. And right now, whatever we are proposing is not an instantaneous change. So we collect the data for, especially with the telematics data, we collect the data for 4 weeks and then propose a change that has to be implemented. So it is a plan generation for recurring patterns. There was interesting analysis when we started implementing the system. The state came to us as well to see that, hey, we are having some problems with ramps, and can you come up with a performance measure for motorways when they intersect the signals, what is going on. So we came up with a new performance measure which measures what percentage of effective queue length is being occupied by the queues that are being generated. So essentially what we do is we project for every hour how the queue is extending, and we try to find out whether it is actually exceeding the amount of queue boundary, amount of space that is available. And again, as I said, there are different optimization functions that are required, and if you are going towards a direction where you don't have queue spaces left, then you might have to assign more green or reduce the cycle length. So this enables you to identify the problem and then design the solution rather than one solution fits all. So this was an interesting project which we have been working on. So this is just a quick overview of what the tool looks like. Essentially, we have two modes. There's a city engineer mode and a city administrator mode. In city administrator mode, we try to give a big picture idea. But in terms of the city engineer mode, you go in and select your specific city. And then you can select, look at the date and time, and start analyzing your system. And it'll start telling you what your demand patterns are and what your delays are for that system, and so forth. So if you select a specific corridor, you can start looking at the delay patterns, and then you can also further, and if I bring it back over here, you can look at the signal timing suggestions for a specific corridor as well. So this is the tool which we have developed, and this tool can be expanded if you have additional data sets available. So if you have additional cameras, you can start integrating it with the tool itself. To kind of wrap up the conversation and wrap up the discussion and open up the conversation, I just want to make sure that any agency which is trying to set up a system and any system which is proposed to you, one of the questions you should be asking is it able to use all the data which is available? Do you have to buy more hardware? If you have to buy more hardware, is it justified to buy more hardware depending on what you can do with the system? I would strongly recommend you to also not just increase the number of dashboards you have available to you. If it requires a lot of engineers' time to identify the problems, you don't want to have another set of dashboards and which are requiring more of your person's time, because person's time is itself limited. And the other question you might want to answer from any system is, does it let you define your objectives, whether it is whether you have to have questions like, can it limit the queue not to spill back on a specific signal corridor, and can you easily justify what the solutions are? So is it an open box system? So essentially, any solution which is answering a lot of these questions is a good solution. So it's not that Signal IQ is the only solution out there. There might be other solutions, but that's what we are aiming for. And again, if it's costing more than hiring an expert, it might not be a very cost-effective solution. So I'll end over here and open the floor for more questions, and would be happy to answer any which are available. Okay. Any questions, folks? So I see that there are certain questions which are in the chat as well. I have tried to cover some of them. So the question, how frequently the offset tuning is done? Essentially, we keep a tab on those two performance measures, which one is the slowness, another one is probability of stopping. If we see a big drop, we do the offset tuning in that. Then we do. So it is continuously monitor, identify a problem, and then solve it is our solution. How is pedestrian signal timing managed in the system? So as I said, at least in US, if you have a pedestrian present, there it impacts your minimum cycle lengths and the minimum green times. So then it would completely depend on whether you want to bring up your pedestrian call every cycle or not. So that is essentially a constraint which is made available. Are you able to gather live data with from AV? I think I answered this question. We are able to process a lot of data from videos, but again, it depends on the number of videos you have got. So essentially, we are using around 4 GPUs to process around 100 cameras. So if you have more cameras, you just have to buy more compute. What are the tuning parameters required? The tuning parameters essentially are required is one is what are the constraints. So for example, if there is a minimum cycle length which is required, if there is a specific intersection where you don't want the coordination platoon to stop, if there are some certain things like that, if there is a very small queue length, like if there is a geometric constraint in terms of queue length, that is required. But other than that, we involve humans in every, like they can see every decision which has been made, and they can tweak those parameters. So we call it more of a human in the loop system rather than or not human in the loop, but expert in the loop system. So they can take a look at it and fine tune a few things. All right. Any other questions? Okay.
Anish sir, you want to add something? Shahim sir? Hello, Shahim sir?
Ma'am, Saha is left for a meeting.
Okay, yeah. So I think we don't have any more questions.
Okay.
Ashwati, please.
Yes, ma'am. That was a nice presentation. Thank you, sir. Now I request Dr. Anila Cyril, Junior Scientist, to propose the vote of thanks.
Dear one and all, it is my honor to propose a vote of thanks for today's Transtech Talk on leveraging CAV data for scalable signal retiming, the Signal IQ framework. At the outset, I extend our heartfelt gratitude to Dr. Anuj Sharma, Professor, Department of Civil Construction and Environmental Engineering, Iowa State University, for delivering an insightful session. His presentation offered a very detailed understanding of how the CAV data can revolutionize signal retiming practices across urban networks. The case studies shared today effectively illustrated how matrices like delays, then queue length, and arrival on green ratios can be used to improve the travel time reliability and safety across large scale networks. Also, the talk underscored the importance of embracing scalable, cost effective, and digitally enabled solutions to strengthen modern traffic signal operations. I would also like to express our sincere appreciation to ATPIO for their support in arranging today's distinguished speaker. Their continued collaborations adds immense value to these knowledge sharing platforms. A special note of thanks is due to our director, division heads, and the organizing team for their consistent guidance and efficient coordination, which ensured the smooth conduct of this program. Finally, I convey our gratitude to all the participants for your presence and active engagement throughout. Your interest and enthusiasm make these discussions enriching and purposeful. Once again, thank you, Dr. Anuj Sharma, for your exceptional contribution. We look forward to many more such enlightening sessions in the future. Thank you all.
Thank you.